Hello all, welcome to this tutorial on problems of probability. Till now, you have successfully completed 2 weeks of lecture sessions. By now, it should be clear to you that the basic ideas of probability are needed in understanding the ideas of machine learning. So, to reinforce that, we have selected a few problems which will indicate some of the important aspects of probability. So we will go through each of those problems. The main idea, as I told you, is to reinforce that, okay, now these ideas of probability can be used whenever necessary in the coming discussions that happens during the course. So without further delay, so let's proceed. So I'll take a very first problem as a very simple one. The problem goes something like this. You have four letters. Okay, letter 1, letter 2, letter 3, letter 4. Okay, you have letters and then you have four envelopes on which the address have been written. Okay, so now you have four letters and then you have four envelopes. Now you can randomly put a letter into an envelope. Now, when this is the case, now what is the probability that exactly three letters are in correct envelopes? Okay. So, out of four, three are in correct envelope. So, you have four letters. Exactly three of them should be on the correct envelope. Now, this is a very interesting question. The reason being, see, if I have four envelopes and four letters, if three of them are in correct envelopes, then the fourth one has to be there. Correct? So the probability of this is actually 0. Why exactly 3 he's saying. Okay, exactly 3, no, it is not possible. Okay, exactly 2 I would have computed. Exactly 3, if 3 of them is in correct envelope, then the fourth one has to be in the correct envelope properly. Okay, so now therefore the probability of this specific event is 0. Okay, now the answer is 0. So I'll not be going into the detailed writing of detailed explanation, but intuitively now it makes sense to us. Okay. So now this is the first simple problem that we have taken. So now let's go to the next problem. Now the problem is like this. A bag contains two coins. Okay. You have a small bag, it contains two coins. Now one coin is a fair coin. Now what do I mean by fair coin? Is that if you toss it, the probability of heads and the probability of tails, those are the two outcomes that are there. They have equal probabilities. Now, by now, you should be knowing the overall idea of this coin tossing and what is the probability and stuff, which has been discussed also. Now, on the other hand, you have the second coin, now, which has both the heads. Okay. Now, you have a fair coin, okay, and then you have a second coin, which is a biased coin, now, in which both are heads. Okay. So now, then what happens is you randomly pick a coin from that bag and then you toss it. Okay, you randomly pick a coin and then toss it. Now, what is the probability that it's a fair coin? Is the first question. The second question is you toss the same coin again, it gives you tails. Then what is the probability that it's a fair coin? Okay. Now, to understand this, we should be going ahead and using a very important Bayes rule. So now let's I have coin 1. Let's call it a fair coin. Coin 2, let's call it a biased coin. And what are the outcomes that are possible? The outcomes that are possible are either you can get a head. Okay, let's indicate this head by H, and tail, let's indicate it by T. Now, what is that we have? Now, already I have tossed a coin and then head has come up. I already know something has happened. Now, on that evidence, what is the probability that it's a fair coin given head has already occurred? Okay. So, now we'll be using Bayes rule and then the total of probability together. It will be probability of heads given a fair coin into probability of choosing a fair coin. This is the numerator divided by, in the denominator we have two terms. Now probability of head, now given that it's a fair coin, into probability of fair, plus the second term is probability that I have a head given biased coin into probability of getting a biased coin. Okay. This now probability of head when you have a fair coin. Now it's a fair coin, therefore it has to be 0.5. Now then probability of you getting a fair coin. Now that means when you take a coin from the bag, what is the probability of you getting a fair coin? There are two outcomes. So one of them being fair, so it has to be 0.5 divided by this 0.5 into 0.5 plus. Now when you have a biased coin, when you know that you have a biased coin, what is the probability that you get head? Now it is 1 into, what is the probability that you get a biased coin? Okay, that is 0.5. Now if you compute this, this is 1 over 3. That means that when you know that you have got a head, the probability that the coin that you have in hand is a fair coin is 1/3. Okay, now this is for the first one. What is the probability that it's a fair coin? The second one is you toss the same coin. Now whatever coin that you have got, okay, you toss the same coin and then it shows a tail. Okay, so in that case, what is the probability that it has to be a fair coin? Now intuitively, you know that it has to be 1. But the question is, can you obtain it in terms of equations? I will leave it up to you. There is probability that the coin that I have is a fair coin given a head and then a tail has occurred. Can you substitute this? Now, this is the probability of getting head and tail given a fair coin into probability of getting a fair coin divided by, I have two terms again here, that is probability of head and tail, the coin is fair, into probability of fair plus probability of getting head and tail by knowing that it's a biased into probability of a biased coin. See, now here this is the denominator, the sum of these two terms. Now probability of getting head and a tail from a biased coin. No, it is not possible at all. Why? A biased coin has two heads in our case. So this will be 0. This 0 into something, so it is 0. This plus 0, so it's the same term. So this term and this term will get cancelled. So it has to be a fair coin. So it's 1. It's a for sure. So once I get a head and then I toss it again and get a tail. Okay. Now the one that I'm getting is a fair coin. On the other hand, can you compute in addition to this? You take a coin randomly and toss it, you get a tail. What is the probability that it's a fair coin? Can you compute it in a similar manner? I will leave it. Okay. Now this is how you try to understand the calculation of probability. So now let's go further. The next question that we have in hand is, now you have a random variable. Now to be more specific, now this is a continuous random variable. I should have mentioned that. You have a continuous random variable. Okay. And then for a continuous random variable, you have a density. This is the density. Okay. And the density is between 0 and 1. Okay. That's the range of this. Okay. So now the question is, find the value of k. So now let's try to understand. This is a very interesting question altogether. Now which will give us a very interesting idea. For example, for this random variable x, I can have a distribution function. Now a distribution function is from R to 0, 1. Now you know that the distribution function or a push forward function which is there is actually a probability measure. Okay, you know it. So now and then, in the similar hand, you know that the distribution function can be evaluated at a given point. Now how do you evaluate it? Minus infinity to x, the density function at that point, into dx. Correct? So now you can say that function of infinity, now what it will be? Now it will be minus infinity to infinity px of x dx. Now this has to be 1. 1 equals, and then what is the actual thing? Now this is between 0 and 1 px of x dx. Okay. So now let's substitute the value. Now this is same as 0 to 1 k into 1 minus x into x dx. Now k is independent of x, so we can take it out. Integral of 0 to 1 x minus x square dx. If you integral can be applied to both of this, so you will get x square by 2, this is 1, x cube by 3, 0 to 1. We have to evaluate this. Now this is k 1 by 2 minus 1 by 3. This is k into 1 over 6 is 1, implies k equals to 6. Now, what is the main outcome of this overall thing? Now, if you integrate your density function from minus infinity to infinity, you should get 1. Okay. Now, please remember, I am not saying that for a specific value of x, you will get anything. No, I am saying that you integrate it from minus infinity to infinity, you should get 1. Because of which I would be able to calculate the value of this k. Okay. That is the take home message from this specific problem. Now, after that, it is just, what do you call, the algebra of it. Okay. Now then the overall computation boils down to the algebra. Okay. Okay, good. So now let's take the next question. Now we have already been, even in the class, introduced into the uniform distribution. So let's say that I have a random variable x now, which is a uniform distribution from -1 to 2. Okay. And what is the density for uniform? If X is a uniform from A to B, then the density X is 1 over B minus A. In this case, 1 over 2 minus 1, which is 1 over 3. Okay. This is the density. Fine. Now this density is defined in this between these values. Now I take y, which is mod of x. Now because of which, now tell me what is the probability that x is less than or equal to y? And then what is the probability that x is less than y? Now you might think that both of them are same actually. Hold on. Okay, there is a very nice catch here, which we should understand. So now let's try to understand this. For any number, for any real number x, whenever I say number, no, throughout the course, unless specified, we are dealing with real numbers. Okay. For any real number x, x is always less than or equal to x for sure, right? Okay. Now let's say that x is minus 1. Minus 1 is less than mod of minus 1. Minus 1 is less than 1. This is true, even if it is a negative value. If x takes a negative value. If x takes a positive value, let's say that x is 1. Now 1 is less than modulus of 1, less than or equal to, yes, it is trivially holds good. Now, that means that irrespective of the value, it holds. Okay, let it be positive or let it be negative. So now this holds, and only when x is negative, x will be less than this. Now you see this and this is different. Now this is valid. This relation is valid for all the values of x, but this relation is only valid when x is negative. So now, therefore, probability that x is less than or equal to y, which is same as the probability that x is less than or equal to modulus of x. This is 1 because it is true for every value. But on the other hand, probability that x is less than y is same as probability that x is less than modulus of, oh sorry, is not equal to here. Okay. So now x is less than modulus of x. Now the effective values that x can take in negative is from 0 to minus 1. Correct? So therefore, now this has to be probability of x less than 0. And the question is, do we know how to calculate this? Yes, we actually know how to calculate this. Now, this is nothing but integral from minus infinity to 0 px of x dx. Now the effective value is minus 1 to 0 1 over 3 dx, which is 1 over 3. See, now I just, please remember this. Okay. Now the key takeaway from this question should be, okay, so now depending on the nature of the function, okay, now please try to understand the equalities. This can change. For one, see what is happening. Just for the other, see what is happening. Okay. Please be vigilant with these kinds of things. Okay. I assume that the takeaway message is clear from this question. Okay. So now let's go to the next question. Now I have a discrete random variable. Okay. Now whenever I have a discrete random variable, this is a mass function. Okay, this is not a density function. Only when, so, but for both of them, we use the same notation, but while using it, you should be very much clear. Okay, depending on what is the random variable at hand. Now, if it is a continuous one, now then it is a density, else it's a mass. Okay, if it is discrete, it's a mass. So now here, so we just need to look at the expectation. Remember expectations? So remember moment generating functions? What is the relationship between moment generating function and expectations? Have a nice recap. Okay. So now always, we are trying to estimate the distribution or the moments of it. Correct? That's what the first premise was. So now we are estimating it. Now the expectation of x, since x is a discrete random variable for all over all x, it is x into px of x. The values that it is taking is, let's say that k equals 1 to 20, this is k into 1 over 20. Okay, now this is 1 over 20 into summation k equals 1 to 20 of k. Now you should be knowing this, 1 over 20 into 20 into 21 by 2. Remember the formula? Sum of n numbers, go back, this is 21 by 2. This is how you calculate the expectation of a discrete random variable. Okay. After that, it's a numericals. Okay, these are algebra. Now let's go to the next question. Now I have a continuous random variable, a uniform distribution from 0, 1. Okay, 0, 1 uniform, so the density will be 1. So now I'm asking you if this is the y. Now y is a function of x now. And then you're trying to find the expectation of y, and y is a function of function of x, sorry. Okay. So do you recall a very interesting proof by the term LOTUS, law of the unconscious statistician? Now it says if you have expectation of a function of x, okay, then how do you do it? Now integrate over it. Now you apply the function at a specific point and then have its density. Okay. Now go back to this and then please try to look at it. Law of the unconscious statistician. It's so common, you don't feel the difference at all. Okay, we'll use it now. Okay, so now what is y? Y equals x square plus 2x plus 1. Now expectation of y equals expectation of this x square plus 2x plus 1. You remember the linearity of expectations? That's the catch. With the linearity of expectations, expectation of x square plus 2 into expectation of x plus expectation of constant 1. Expectation of a constant is a constant itself. Okay. So now this expectation of x, now I have to calculate. Now this expectation of x square. X square is a function of x. So now I will be using this law of the unconscious statistician. So let's calculate each one of them. So expectation of x is 0 to 1 x into px of x density dx, which is integral 0 to 1 x dx. Why? Because the density is 1. This is x square by 2 at 0, 1. This is half. Expectation of x is half. Now you have to compute expectation of x square. How do you compute? Now you take the integral and then you evaluate fx. That is integral 0 to 1 x square into the density of it. See, now it is so natural. Okay, from here, so x is there, x square is there. That is why it is called as unconscious statistician. You don't even need to be conscious. A statistician, whenever he is applying this, he don't even need to be conscious. Unconsciously, he can just apply this and take it from me. The proof is 3 pages. Okay, a nice proof is there in Wikipedia. Very easy for showing it for a discrete case. Please go ahead, have a look at it. It's interesting. Now this is integral 0 to 1 x square dx x cube by 3 divided by 0 1. This is 1 over 3. Now then you have everything. Now let's put them together. Expectation of y equals 1 over 3 plus 2 into half plus 1. This is 7 by 3. Okay. The key takeaways from this is, how do you apply this law of the unconscious statistician and the linearity of expectations? Okay. Now this example is designed for understanding the linearity of expectations and expectation of a constant, and then law of the unconscious statistician. That was the aim of this problem. Okay. Let's proceed. The next question that we have in hand is, let x be a random variable. See, I'm not specifying that now what it has to be. Okay. Now this we are generically using for continuous random variable or discrete random variable. So if x is a random variable and y is a function of x. See, expectation of x is a constant. Variance of x is also a constant. Therefore, the square root of it is a constant. So this is x minus some constant divided by some other constant. Now, whatever it might be. Okay. Now, given y, which is a function of x now compute mean and variance of it. Okay. That's the problem at hand. Okay. So now let's define, let's make it easy. Let's say expectation of x is, let's call it by mu. Easy. So, and then sigma square, no, okay, I should have written the other way. The variance of x, let's use sigma square. And therefore, implies the square root of variance, yes, sigma. Now, what my y will be? Now, my y will be x minus mu divided by. Now, this is straightforward indication that there is, I just rewrote this so that you don't see x and then again do some kind of other blunders of calculations. So now I have to find the mean. That is, expectation of y is expectation of this whole thing, x minus mu divided by sigma. So now expectation of ax is a into expectation of x. Now 1 over sigma is a constant. I can take it out. Okay. This is 1 over sigma into expectation of x minus mu. Now by the linearity of expectations, I can, this is expectation of x minus expectation of mu. Now we know that expectation of a constant is constant itself. Therefore, this will be 1 over sigma into mu minus mu. This will be 0. Okay. Now expectation of x, I have said that it is mu. And here mu is a constant. Expectation of a constant is the constant itself. So mu minus mu is 0. So 0 into anything is 0. So I got 0 over here. Okay. So now, then I need to compute the variance. Okay. Now variance of y, now which is variance of x minus mu divided by sigma. Now, variance of something into constant. Okay. Now, if variance of ax is equal to a square into variance of x. Okay. Now I can use it 1 over sigma square into variance of x minus mu. Okay. So now, okay, maybe I should write it somewhere. Okay, I'll write these formulas used somewhere. Expectation. Okay. Let me use some other color. Some which formula I'm using. Expectation of x plus y. If you have, these are the formulas not related to this. This is expectation of x plus expectation of y. Okay, linearity of expectations. And again, you have, this is the first one. Expectation of a constant is constant. Then you have expectation of ax is a into expectation of x. See, expectation of x is a constant. It's a scalar. Okay, please remember that. Similarly, what I have used here, okay, the same thing. Now this is, I have used variance of ax equals a square into variance of x, and the other one that I am using is variance of x plus a equals variance of x. Now this is variance of x plus some constant minus mu. Now, therefore this will be 1 over sigma square into variance of x. Now this is 1 over sigma square. Now what is variance of x? How did I define it? I used sigma square. Therefore this will be square. Therefore it is 1. So y is a random variable which is function of x with mean 0 and variance 1. Okay. So now what are the key takeaways from this? Now trying to understand applying expectations and trying to understand how do you apply the equations of variance. That is the key takeaway from this specific question. Okay, I think that has been pinned properly. Okay, so now let's go to the next question, which is a fairly simple one. Now in this question, now what is that I'm having is, I'm having xy are IID binary random variable. Now IID, you know what is independent and identically distributed. We discuss it in quite a length. Remember that, very important assumption. Now to understand that assumption itself, we are trying to handle this question. Okay. Now x and y are IID binary random variables taking only two values, 0 and 1. That means that this random variable takes only two values. Okay. Now the probability of taking one value, that is 0, is 1 minus p, and the probability of taking 1 is p. Now if z that you have is x plus y, what is the mass function of z? Now mass function is at each point, now what is the values, what is the probability that it is having? So now these are discrete random variables. X and y are a discrete random variable. Therefore x plus y will be a discrete random variable. Okay. Now what are the values that z can take? Let's go ahead with this. Z can take value 0, 1, 2. These are the values that z can actually take. Okay. So now we have to find the mass. Now that means that what are the things that you should do? Now pz of 0 you should calculate. Pz of 1 you should calculate. Mass at 2 you should calculate. Okay. So now Pz of 0. Now what do you mean by this? This is probability that z takes the value 0. Now what is z? This is probability that x plus y takes the value 0. Now when will x plus y takes the value 0? when x plus y individually can take only 0 and 1. Now this is possible only when probability that x is 0 and y is 0, correct? This is the only case. Now you see this x and y are IID. Independent is I'm just using the independent feature here. Now this I can write it as probability that x equals to 0 and probability that y equals to 0. Okay. Now what is probability that x equals to 0? The probability that x equals to 0 is 1 minus p. Now, what is the probability that y is equal to 0? Now since x and y are identically distributed, y taking the value 0 is also 1 minus p. Now this is where I'm using the identical part of it. Okay. Previously from here to here I used the independent part of it. Now I'm using the identical part of it. This is 1 minus p whole square. Okay. Now I presume that these minute differences are clear for you. Okay. So now the next value that, okay, now the next is the mass at value 1. Now this is probability that z equals to 1. Now this is probability that x plus y takes the value 1. See, x plus y can takes the value in two different things. Okay. And those two events are disjoint. That is x is equal. So what are the values that it can, okay. Now the two options is x is equal to 0, y is equal to 1. X is equal to 1, y is equal to 0. See, these two events are disjoints. Now whenever, recall the axioms. Now whenever you have disjoint events, now you can add them. This is probability that x is equal to 0, comma, y is equal to 1, plus probability that x is equal to 1, y is equal to 0. Now I think from here you are capable enough to take it. Similarly, the z of 2, this is probability that z takes the value 2, which is probability that x plus y equals to true, which is only possible in the case when x is equal to 1 and y is equal to 1. Okay. Now I have partially solved the problem for you. From here, use the independent and get them into products, and then use the identical, get the numbers and find the final values. Okay. Now this is for you to understand. Now how do you apply the IID assumption that you have? Okay. Now please remember, I'm reiterating. See, don't put calculation emphasis is needed, but understanding which property has been used in which step is very critical in going ahead. Okay. I presume that that is pretty much clear. Okay. So now let's go to the next question. Interesting question in itself. Okay. So now we have a random number generator that generates random numbers uniformly distributed over 0, 1. Okay. Now you ask it, give me a random number, it will give you a random number. Now you ask it for 10 times. Okay. Now you asked it for 10 times and then it gave you 10 numbers. Okay. Let's say that this is x. Okay. You have got 10 instances of them, x1, x2, so on till you got till x10. All of them are sampled IID. Okay. All of them are sampled IIDs from a uniform 0, 1. Again, this question is also to reiterate the idea of IID. Now, what is that I want? Now, I want the probability that the maximum number is less than 0.8. Now, the maximum of these things is less than 0.8. Now, that means that each and every one is less than 0.8. Correct? Now, if let's say that m is the maximum, m is max of x1, x2, so on till x10. Now, if my maximum value is less than 0.8, now which means that individually x1 is less than 0.8, x2 is less than 0.8, so on x10 is less than 0.8. Okay, so now you need the probability of this m less than or equal to 0.8. Now the probability of this is union of these individual things, and these are disjoint. Okay. Oh, no. Sorry, these are sorry for that. No, not that. No, these are IID assumptions. Sorry. Okay, these are IID. Now, therefore, what happens is this is probability that xi less than 0.8. Now you multiply each one of them. So therefore, I'll get 10 here. Now xi taking a value less than 0.8. Now this is, you know this already. From uniform 0, 1, this value will be 0.8 to the power of 10. Now, why is this 0.8? Now, what is this? This is integral 0 to 0.8 x into px of x dx. Okay. Oh, sorry, integral. Sorry for that. Okay. This is integral 0 to 0.8. This is px of x dx. I confused with expectation. Okay. This is 1. Therefore, you get 0.8. This is your distribution calculation. Okay. Sorry, I wrote expectations. Yeah. No. See, this is, as Sir reiterates, no. This is a straightforward indication that we are not AI, which means that we make mistake and immediately we get a feedback and then we correct it. Okay. Good. So now here again, the idea is to understanding the IID assumption. Okay. Now IID is a very important assumption during our discussion. Okay. So let's go to the next question. Let xy be random variables with mean and variance 1, both of them. Okay. Now whenever you get like this, always write it. Expectation of x equals expectation of y equals 0, and then variance is 1. Now that is variance of x equals variance of y equals 1, and then the covariance between x and y is rho. Okay. Now find expectation of x plus y whole square. Okay. Now again, this combines all our ideas on expectations. Expectation of x plus y whole square. This is expectation of x square plus y square plus 2xy. This is expectation of x square plus expectation of y square plus 2 into expectation of xy. Now I don't know. See, if you want to calculate the expectation of x square, okay, I know the law of the unconscious distinction. Now I can integrate and say x into px of x dx. But what is this px of x? I haven't been given. I even don't know what is the effective support of this random variable. Okay. So now with these, I should go ahead. Okay. So now the idea is quite simple. Let's use the variance of x formula. Now, what is variance of x? Now, variance of x is expectation of x square minus expectation of x whole square. Okay. Now we know variance of x is how much? It is given 1 equals expectation of x square minus, do you know expectation of x? Yes, it is 0 square, it is 0, which implies expectation of x square equals 1. Similarly, expectation of y square is also 1. See, now by using this variance formula, which is a new learning in our case, we understood these two things. Okay, now I just need to know expectation of xy. Now, how do I know expectation of xy? Now, we know that the covariance of xy is given by expectation of xy minus expectation of x minus, expectation of x into expectation of y. Now, expectation of x and expectation of y are 0. Now, therefore, this term is 0. Therefore, this I know rho is expectation of xy. Done. I got all the values internally. Now I can substitute them. Expectation of x square is 1 plus y square is 1 plus 2 into rho. This is 2 into 1 plus. This is the expectation of x plus y whole square. See here, I was not knowing the support of the random variables. I was not even knowing their densities or mass for that matter. Okay, now here I'm not even assuming that they are continuous or discrete in any way, and I even don't have the information that they are IID. Now, if you had IID, okay, you would have said something else, you would have got something, but none of that was happening. Okay, by using these given values, we were able to compute this. Now, here the idea is to introduce to the idea of covariance, and then the calculation of variance was the main idea, the additional thing. And this from here to here, we already knew this. This is from the linearity of, from here to here, we already knew this. This is from the linearity of expectations. How do you get this independent value? Okay, that was the main idea in this case. Okay, so good. So now let's go to the next question. Next question is an interesting question, which is on conditional expectations. And here I have x and y are independent. See, I'm not saying they're IID, they're independent random variable with expectation of x is mu1 and expectation of y is mu2. Now give me, okay, if z is x plus y, then what is the expectation z given y? Okay, now let's try to do it. Now this is, what is that I have to find? I have to find expectation of, conditional expectation of z given y. Now this is expectation of x plus y given y. Okay. Now, again, from the linearity of conditional expectations, this I can write it as expectation of x given y plus expectation of y given y. Okay. Now, this is from the linearity of conditional expectations. Now, we need to calculate each one of them here. Expectation of x given y. See, now x and y are independent. Now, therefore, conditioning on y has no impact. It is expectation of x, which I know as mu1. Okay, when independent. So when x and y are independent, we know this. And the next thing is I need the expectation of y given y. We know this is y. Okay, now substituting these back, now this is mu1 plus y. Now here, now we are understanding how do you calculate the conditional expectations under the nature that x and y are independent. Okay. Now, the last problem for our discussion is if x and y are IID, standard Gaussian. Okay, standard normal distribution. Whenever I say standard normal, mean is 0 and variance is 1. Okay, that is what I mean by standard normal. That is x and y are normal 0, 1. Okay, and I have my z equals 3x plus 4y. Now what is expectation of z? This is expectation of, oh sorry, what is the density of z? For density understanding, you should know the expectation and variance. So expectation of 3x plus 4y, the linearity 3 into expectation of x plus 4 into expectation of y. This is 0. Expectation of x is 0 and expectation of y is 0. Okay, and then variance of z is variance of 3x plus 4y. Now what is this? This is variance of 3x plus variance of 4y plus covariance of 3x comma 4y. See, since x and y are independent, the covariance term will go to 0. It will not. So therefore, this is variance of 3x plus variance of 4y. This I know, this is 3 square into variance of x plus 4 square into variance of y. What is variance of x and variance of y? It is 1. Therefore, it is 3 square plus 4 square, which is 25. Therefore, z is a random variable. It's a Gaussian distribution with mean 0 and variance as 25. I think from here, now you should be able to write the density. Now that is Pz of z equals 1 over 2 pi sigma square root of this exp of z minus mu whole square, there is a minus here, divided by 2 sigma square. Okay, now this is 1 over 5 into square root of 2 pi exp of minus z square divided by 50. This is your density function. Okay. Now with this, I conclude today's tutorial on the problems on probability theory. Now the main aim of this tutorial was to give you some of the interesting ideas and how do we use them and when do we use them. Okay, throughout the course, in each of the problem, we have looked at some of the important ideas, and as we go along, now whenever these ideas are needed, we'll be recalling them back and then using the same good old ideas. Okay? These are quite important. I assume that you enjoyed this tutorial on simple problems on probability theory. These were not numerically heavy problems. These were simple calculations for us to indicate the key concepts that are needed during our discussion of this course. I hope you are enjoying the learning. Thank you. We'll meet in the next tutorial. Thank you. Bye-bye.